Hi everyone. This next assignment we're going to be working with populations, and we are going to be looking at how scientists count populations. And as you can imagine, it's pretty hard to count every member of a species, of every single species that exists, right? I mean, they don't go out and count every single oak tree or every single mosquito or even every single elephant out there. They have come up with ways to help them estimate population size, and get it pretty close, pretty good, at least in terms of being able to deal with things like wildlife management and extinction and endangerment and things like that. So that's what we're going to talk about. And this first part, we're going to need to be doing some math. So in order to do that, I'm going to refresh your guys' memory. You're going to be doing some ratios, and you're going to be doing some density calculations. Well, with ratios, you got to remember that ratios are comparing two numbers together, basically. How many of one thing compared to how many of another thing. Okay? So, for an example, we're going to say that we have a cafeteria, and that cafeteria is 9 meters by 9 meters in size. We're going to say in our cafeteria we have 36 people, 27 of them are students, and 9 of them are teachers. Okay, so if I were to ask you just to simply write me a ratio of students to teachers, you would write, okay, there's 27 students and there are 9 teachers. Okay, see how this is 27 and 9, and that can be reduced. So we can reduce those, and our ratio ends up being 3 to 1. Okay, or you can write it 3 to 1. So the ratio is 3 to 1 of students to teachers. Okay, so again, if you have numbers that are reducible, okay, like for example, this one, you can divide each number by 9. So you divide 27 by 9 and get 3. And you divide 9 by 9 and get 1. So you can reduce it down to 3 to 1. So if your numbers are goofy and you can't reduce them, well, then that's just the ratio. But if you can reduce them, you're going to reduce them. Okay? Now, what if we want to calculate the density? Now, density is usually mass over volume. At least that's how we've learned it in science. But density is really any amount of something, number of something, in amount of space. Okay, right? Volume is space. Mass is the amount of weight or amount of mass. So when we're doing with people, we're going to say the number of people or the number of organisms over the amount of space. Okay, so we have measurements for the cafeteria, and it's 9 meters by 9 meters. And if you remember correctly, the area, I'm running out of room, area equals length times width. And it gives you a unit squared measurement. Okay, so since we have meters, your answer is going to be meters squared. So 9 times 9, oops, where am I going to go? 9 times 9 equals 81 meters squared. Okay, so our space, we have 81 square meters. So that's our space, and the number of people is 36. Okay, now again, you're going to look even for this because this is a ratio. Okay, we are calculating the density, but in terms of populations, we're really looking at ratios. So we have 36 and 81, and again, these numbers are divisible by 9 in this case. Okay, so we can divide or reduce it to 4 people per, that line kind of means per 9 meters squared, right? Because if you divide 36 by 9, you get 4. You divide 81 by 9, you get 9. Okay, so one thing that's important here, is that when you're comparing things, you have to add the units. 4 people per every 9 meters. So that's the estimate of the density of how many people are in some certain space. And so in this case, in that cafeteria, for every 9 square meters, you have 4 people. Okay, and so you're going to do this with organisms in a space. Now, the first thing that we're doing is called quadrant sampling. And this is where scientists kind of, in the field, they will literally stake out an area with poles and flags and rope it off. And then they will divide it up into space. And then they will look and count all the organisms in that one area. And the reason they do this is because they cannot get to the entire, area in order to count every single organism. But this is, but you can estimate based on what's in these certain quadrants, because you can assume that they're going to be similar across a broader range. Okay. Now this obviously only works really well for organisms that do not move very well. Because if you have organisms that are constantly moving between these quadrants, it's not going to be very effective if you count it here and then they move to the next one and you count it in the next one. So this method, this quadrant sampling that we're doing right now, is really only effective with organisms that stay put, like trees and plant lives. And you're going to be looking at echinoderms, which are sea stars and sand dollars, and they don't move very fast at all. So it works pretty well for them. Okay. So again, you're going to be counting things and say, this is 3 feet. Okay. We're going to use 3 feet. And this is 9 feet. Okay, and I know I did not draw these to scale, but we can just assume that this is 3, 3, and 3. So every one area is 3 times 3, or 9 square feet. Okay, this whole thing, if you're going to count the whole thing, it's 3 feet tall by 3 plus 3 plus 3, 9 feet wide, or 27 square feet. Okay, so you're going to be just using different numbers, kind of playing with the calculations. It might ask you to look at 2 of these, in which case it would be 6 feet on one side, so it would be 3 times 6. It just depends, okay, but always remember the area equals length times width, and the unit you get is going to be a squared unit. Okay. All right. I think that's all you need to know for this next part. So let me know if you have any questions.